We first have the data members for the myLinkedList class. So here we're going to have references to both the header and the tail nodes. We'll also keep track of the size in a data member. That way, whenever we implement the size method, this can be done in constant time. We also have an additional data field that we're going to talk about, and this is used to help the iterator determine if there were changes in our collection. Because if you remember, if there are changes to the collection, then the iterator is no longer valid. So we're going to talk about another data field that helps us with detecting these changes. This data member is called ModCount, and this is going to keep track of the number of changes made to the linked list ever since the linked list was created. So every time we call the add or remove method from the linked list, we're going to update this ModCount variable. The idea with this is that whenever we create an iterator, that iterator is going to store the current value of ModCount of that collection. And every time the iterator is going to call a method, such as next or remove, the iterator is going to check its value for ModCount and compare it with the current value of ModCount for the entire collection. If they don't match, which means the linked list was modified after the iterator was created, the iterator should not be valid anymore. So it will actually throw a concurrent modification exception, which just simply means we made changes to the linked list after the iterator was created, so that iterator is no longer valid. You're not allowed to call next or remove after making changes to the list. We have a declaration of the private nested node class here. So we have three instance variables. We have the data that the node is going to store, and then we have reference variables that correspond to our previous node and our next node. And then we have a constructor for our node class, so we can initialize the data, the links to the previous and next nodes. You may have noticed something odd about the reference variables in the node class, in that all the data members were public. Normally they're private, but this is not a typo. This is intentional. And this is because the members in a nested class are visible even in the outer class. So our outer class is still going to see those members inside of the node class. And because the node class was private, it actually really doesn't matter if we make the members private or public, because none of the classes outside of the myLinkedList class can even see it in the first place. So we just decided to make it public because we could. Now I should also mention that because the node class is a nested class in here, the myLinkedList methods can see all the data members. So they can see everything in there, and classes that are outside of it can't see the node class at all. So this implementation is perfectly fine because all the methods in the myLink class can see the data and the next and the previous reference variables. There's no issue with that at all, and all the classes outside of the myLink class can't see anything in the node class anyway. As we saw in the code, the rest of the myLink class just contains the rest of the code. It contains the constructor, it contains the full implementation, it contains a host of different methods. So this includes things like clearing the list, getting the size of the list, checking if the list is empty, adding nodes, removing nodes, getting the values of nodes, setting the values of nodes, and creating and using iterators. And most of these methods only have one line of code. Let's take a closer look at the doClear method. So the idea with this is we're pretty much initializing the entire list. We're clearing all the contents of the list, and we're pretty much just starting with an empty list. So we start by creating the header and tail nodes, and this is noted with the begin marker right here and the end marker right here. So we're creating new nodes, and then we see in the constructor portion of it, or the parameters of what we're passing here. So begin marker just is completely blank because there aren't any other nodes. With the end marker, we're noting that the previous node to end marker is begin marker, and then the next line is where we set begin marker dot next to the end marker. So that way we can have begin marker go to end marker. and then we would set the size to 0 because even though we have header and tail nodes, we don't have any actual nodes in the list. And then finally, we increment our mod count because we did make a change to our list. Let's take a look at how we would add nodes in our linked list. So let's say we want to add a new node, and let's say the data in here is x, and we're going to put it between nodes p and p.prev. So let me try to draw this for you. So let's say we have a node here that is p.prev. And then we have a node over here that contains p. And these nodes are connected to each other, so p.prev.next is going to point to p. And this p.prev, well, that's going to point over here to whatever p.prev is. So we need to create a new node. So I'm going to put that down here. And this is going to contain x, where the previous of this node is going to point to p.prev. So we'll do that right here. Okay. And the next of x is going to point to p. All right, so we'll do that here. The next thing we need to do is change where p.prev.next is pointing to. It should point to the new node, but right now it's pointing to p. So let's get rid of that. And what I'm going to do is I'm just going to say this is gone. We're just going to put a red squiggly line there. So that's no longer there. And instead, we're going to have p.prev point to x. And then we need to change p.prev to point to the new node. So this link is gone. And we're now going to have p point to x. And that's it. And that would take care of adding x in between p.prev and p. So let's take a look at some code for this. So here's a method called add before that's in our code. So here's how it would look like. So we would create the new node, which is we're doing this first line. So that's going to initialize the previous and next reference variables for the new node, and our data is x. We'll then set new node.prev.next to the new node. That's having p.prev point to the new node. And then finally, we need to take the previous of p and have it point to the new node. And that takes care of adding our node. So now let's talk about how we would remove nodes. So let's say we want to remove a node p. So we're going to draw some nodes up here. So we're going to remove p. And to do this, we need some other nodes. So I'm going to put over here p.next. And over here, I'm going to put p.prev. Close enough. And they are connected to each other. So we have something like this, because the next and previous reference variables are set this way, so they're connected to each other as so. So what we need to do is we have to make a couple of changes to the links. In fact, we only need to make 2 different changes to our links to make sure that nothing can access p. Because once that happens, the node p would be eligible to be reclaimed by the garbage collector. So what we first have to do is change p.prev.next to p.next. So what we're saying here is this next link here is gone. So we've got to make that go away. And we need to have its next point to p.next. And then we need to change p.next.prev. So right now it's pointing to p, so we need to get rid of this link right here. And we need to have its previous point to p.prev, like this. And what that does is we see that now p.prev and p.next point to each other, so there's no way we have any node that can directly access p anymore. If we traverse through this list, p gets skipped, so eventually the garbage collector will detect that and remove it from the linked list.